Myself, Vicky Quad from ARK Info Solutions, and I am working in ARK from 2024, year 2024 as an application engineer in the low frequency domain. So our today's topic is the silent driver, how power electronics moves electric vehicle. So you can see here the power electronics. So this complete webinar is based on the power electronic devices, how power electronics helps electric vehicles to move and how it controls the actual motor strategies, how the controller strategies, how the inverter is work, how your converter is work. So all these possibilities that we can see in this webinar and explore those topics regarding the power electronic component. So first we will see some ANSYS introductions about the what are the capabilities of ANSYS and what are the domains in which the simulation software you can use. So here the one portfolio like the ANSYS is the number one in the simulation industry. So it is the very big near to the competitor also. It has the around 6,000 globally employees are there and their revenue is also there. And ANSYS majorly gives their revenue in the R&D department. Around 20 to 30% revenue is going to the R&D section to improve the softwares because for the ANSYS softwares, each year the two versions has been released, the R1 and R2, and each one has its updation values like sometimes the solver get updated, sometimes to get the better accuracy and to catch the real-time conditions. Next, these are the acquisitions of ANSYS. Uh, Like here, first Fluent is there, and now the all the simulation softwares are there regarding the different industries like the aerospace is there, defense, mechanical, electronics, semiconductor, optics. So these are the various industries, and for all those industries, the simulation software as the ANSYS provides. And ANSYS is basically the physics-based simulation. It uses the physics like for the industries of the aerospace and defense, automotive, energy, healthcare sectors, high-tech consumer electronic sector. Like you can see the wireless charging, 5G technology, the triple IoT, the electrifications, the autonomous vehicles, like the ADAS vehicles are there. Right? You can see the self-driver vehicles. You can use the name. And this is the physics-based simulations, and it has the different physics. Like the first one is the structure, which completely based on the mechanical physics, how the mechanical things are work, and what are the capabilities that it includes for the reliability in terms of the mechanical strategy. There's the fluid section is there for the thermal analysis or the fluid flow analysis. That you can see here. Suppose your electric vehicle is there. Now you want to perform the aerodynamic analysis. How your external, how the flow is there on the exterior body of the vehicle. So you can analyze that flow behavior, how the turbulence is there. So that kind of flow behavior, what are the forces that acts during the running conditions. So that's might you can see under the fluid physics. Then the electronics is there. So in electronics, the two physics are there, the low frequency and high frequency. So in low frequency, we are mostly cover the electric vehicles part. Next, the semiconductor, optics, 3D design, and photonics. So each one has the different physics, and the different physics has the different ANSYS software. This is the complete portfolio about the ANSYS. Like here, the autonomous vehicle simulation, the Connect tools, the Granta tools, which use for the study regarding the material sections in the electronics, semiconductor structures tools, also their fluids, mission engineering, cloud. This is the cloud-based platforms are there, the optics, the embedded software. So each one has their different software and each one has its own capability, own significance of its own software. Like the electronics has the different capabilities. Semiconductor used for the semiconductor purposes. Structure used for the reliability, the mechanical reliability. Fluid is used for the thermal analysis of any of the components. And these are the world-class companies which leveraging the ANSYS platform. Like in the every sector, the ANSYS software is used by the top 500 companies. Like the Airbus is used in terms of the air. or Lufthansa is there in the aerospace sector, in the energy sector, the ABB, Hitachi, the Volvos are there. In the consumer electronics, the companies like Samsung, TSMC are there. In the automotive sector, the Isuzu, Mercedes. So these are the companies that leverage the ANSYS multi-physics software. So multi-physics means they are not using only the one physics like the electronics physics or the thermal physics or the mechanical physics. They are using the multi-physics to see the how our product is behave in the real world application. These are the academic customers also. It includes the IITs, NITs, various IITs and NIITs inside the India. Like BITS Pilani is there, the top private universities also there, the Manipal University. You can see. First, we will see the product line. Means in ANSYS low frequency, what are the products that comes under the low frequency domain? So in low frequency, the Maxwell is there, MotorCAD, Simplorer, and iSpec. These are the four tools that comes under the low frequency domain. So low frequency domain, it is for the electrical applications. What are the electrical appliances are there? So you can simulate those electrical appliances in the ANSYS Maxwell. Next, the MotorCAD is there for the motor technology. Any type of motor that you want to develop, you can simulate any type of motor. Multi-physics motor capabilities that includes under the MotorCAD tool. Next, the simpler is there. The simpler is basically for the power electronics components. Like if you have your circuit, so you can design your circuit and control your strategy. Design your suppose for the electric vehicles, you can design your converter, your inverter. You can define the control strategy, how you can control your motor. What are the current that comes from the battery, and what is the input current value that you might to give to the motor. So that control strategy that you want to develop, you can develop the control strategy inside the Simplorer. Next, the iSpec is there for the thermal calculations of any of the electronic components. And these are the applications that comes like the electric machines, transformer, actuators, wireless power transfer, induction, heatings, electrification, and major role of the low frequency tools comes under the electrification part. So in electrification part, the power electronics, you can see the power electronics is the brain of electric. In the power electronic components, the whole strategy that you can develop, controller strategy, how your in actual how your electric vehicles can perform. So it gives the signals, it receives the signals from the input, whatever the input that you give, it receives the signal and then gives the signal to the battery, the motor, operate on these particular load conditions, cooperate on this about the road conditions, what are the conditions are there, what are the input that you required, what are the output that you required on the basis of that it controls the strategy. There are the power electronic component. Here the inverter thermal management systems that you can see. You can design your inverter and see the thermal calculations of the inverter circuit, the semiconductor. This is the basically the electrothermal analysis. It includes the two physics. It doesn't include only one physics. The electronics as well as the thermal physics also include. The inverter circuit, which is the your control system. How actually you can control your motor or your device. Like if electric vehicles is there, you have to control your motor. Like you have to draw the current from the battery and provide the current to the motor. So first the inverter or your control system drives the current from the battery part. Then on the input values that you give to the controller, like if you press the brake pedal, then it gives the signal to that reduce the current value so that the motor RPM get reduced. So that control strategy. If you press the acceleration pedal, then the current value is need to be increased by the battery. Then the higher amount of current need to provide to the motor section to increase the RPM. So that type of control strategy that you have to develop inside the Simplorer. Next, the converter is also there. The inverter surge and conduction. You can perform the EMIMC analysis also inside the Simplorer too. Now, this is the agenda for the today's power electronics webinar. Is first we see what is the power electronics and its role and challenges. What are the challenges and what are the problem statements are there? Next, power electronic solutions. So, what are the solutions the ANSYS has regarding the power electronics components, like the power converter analysis, power semiconductor modules are the electromagnetic component design, PCB and power electronics, which is basically focusing on the EMIMC analysis, the electromagnetic induction and compatibility testing, how your electric noise, then the PWM converter. PWM converter is basically used for the your motor, how your motor can control. So for that, the PWM strategy is there. Next, we see the one of the examples of the multi-physics like the electrothermal design. Take the electronic reliability. Is your component is reliable for the both physics? Like not only for the one physics, you have to design the components in a such a way that it can reliable for the both physics. Suppose one of the extreme conditions that comes during the electronics phase or electrical phase. So that conditions that might be sustained by your product also caused by the thermal also. So that thermal conditions also get sustained by the components. Then the embedded control system that we can see. And next we'll see the practical demo on the software also. How your power electron component is designed and how you can perform the analysis on the ANSYS software. So now we will start the session from here. Now you can see the power electronics is everywhere. Any of the electronic components that you might see, so you can see the power electronic components are there. So the IGBTs, MOSFETs are there. The various power electronic components are there. The diodes are there. The rectifier circuit. So these are the power electronic components you might see everywhere. And you can see that the 70% of the electricity is processed by the power electronics today. Because if we are not using the power electronics component to process the electricity, so most of the electricity is getting wasted. So we have to control the power supply. Like we are giving any power to any device. Like we have to give the power to your motor. So it doesn't mean like you have to make the direct connection between the battery and the your motor. So you have to incorporate the inverter circuit, your control strategy in between the battery and the motor. So this kind of control strategy uses the and get the best output. Best output means it uses the efficient value of the energy to give and to achieve those output. You have to save the energy also. If you are not using the power electronics component, most of the electricity is getting wasted. Like if we need the 10 kilowatt of energy, if any application, we have to run this application, and for that the 10 kilowatt energy is needed. So if you are using the power electronics components, we require only the 10 kilowatt energy. Some losses also be there, but if you are not using the power electronic component, we require might be 15 kilowatt or the 20 kilowatt energy. The efficiency is nearly go below 40%, 50% energy efficiency is there. So we have to maximize the energy efficiency. For that, we have to use the best control strategy. So whenever the power is needed, whenever the higher power is needed, we have to give the higher energy. So that control strategy you can see here. And power electronics for the transformation that you can see. This is the electric vehicle example is there. You can see this is your transmission, this is your PMSM motor, this is your traction inverter, and this is your battery. Now you can see here the battery is connected to the traction inverter, and then this inverter is connected to the PMSM motor. Means this is your actually your driver. This one is your driver, like PMSM motor is your driver, and then it connects to the transmission to rotate the wheel. Like when you are giving the signal, like when you press the accelerator pedal, you are giving the signal to the your traction inverter, and then traction inverter what it does, it draws the current from the battery, calculate the amount of current. If you press the acceleration, it calculate the amount of current, what amount of current you need to drive your motor or your vehicle at those particular speed. So it draws the current from the battery and supply it to the PMSO motor to achieve those RPM values. Like if you want to perform or if you want to run your vehicle on the 4,000 or 5,000 RPM, so it draws the your traction control or your control strategy draws the current from the battery and supply it to your PMSM motor. Now we have the fast charging station. Like here, the power electronics used in electric vehicles, hybrid or plug-in hybrid mode is also there. In the electric vehicles, the hybrid it contains the engine as well as the battery and your electric motor is also there. In the railways, off-road vehicles, the electric aircraft is also there. The electric ship, the spacecraft is also there. So means whenever you have to give the power supply, whenever you have to control the your applications, you need the power electronic components are there. And you have to use the power electronic components to gain and achieve the maximize energy efficiency. And this is the overview of one of the problem. Like this is your battery component. It includes your rectifier circuit is also there. This is your cable component, and this is your power electronics component. Like it includes the DC to DC converter plus OBC is your onboard charger, your DC bus. This is the voltage. This is your inverter circuit. Now, what are the current draws from the battery? It goes into the inverter section, then it converts is in the significant form, then it goes to the three-phase AC. This is your this traction motor is run on suppose this is PMSM motor. This is run on the three-phase AC. So this DC voltage converted into the AC one and this three-phase AC is supplied to the traction motor to run the motor. And you can upload your load also here. Now the zero is there. So zero means it doesn't have the no power load condition. So if you want to add the power condition, means the load conditions that you can add the load conditions also. So this control strategy you can see these phases are connected each other means we are simply using here the star connection windings is there. So this is basically the overview of how you can use the electromagnetic PCB and the power semiconductors to power your electric vehicles or to develop your control strategy to run your electric vehicle. Now, what are the goals that we are going to chase down by using the power electronics components? We have to use the performance. Like we need to keep the high power density, the higher efficiency, and the lifetime is also longer. We have to chase down the reliability purpose. We have to increase the reliability, the thermal reliability. So whenever the extreme condition is there, suppose uh, in the meantime, suppose any time like the thermal condition is going beyond the limit value. So at that limit also the temperature values can sustain by the your power electronics component. So it can stop the breakage of your system or stop the working of your system. So you might have to check the thermal reliability, the MINC analysis as well as the structural reliability. You have to check for your components so it can sustain the extreme conditions and working during the that extreme conditions also. So for that we have to check at each parameters, check at extreme condition, then the low cost. So what is the use of this power electronics? The failure detection. You have to detect the failure. Suppose any of the components might be failed during the running conditions. So you can change your conditions or change that parameters in a different way. You can add those parameters in a different way in your system. So you can see at which point the failure occurs and which point the failure might be occurred that you can check here inside the simulation. And what is the use of that simulation is that it doesn't need any physical prototype. Here you can see simulation led design can significantly reduce the number of physical prototypes. Suppose what happens if you are designing any of the component. So that time you need to build your prototype, then test your prototype. And next, if you can see like you have to do the modifications, then again you have to do the modifications, then you have to build the product. So this again and again to build the physical prototype is so costly. So that's why the in industry the various commercial applications are used by the simulation industry. So that's they reduce their price or reduce their cost for the overall physical prototype development. So they do the whatever the modifications they have to do, whatever the optometrics that they want to use, what are the optimization techniques that they have, they can use inside the software and they can perform the simulation like the real world condition in the inside the software. And then when they reach the one optimized stage, then they build their physical prototype and test that in the actual condition. So they can validate your results with your simulation results and with the actual one results. So that's basically the use of that simulation software. Now in power electronics solutions, the core modules are there. Basically the electromagnetics one is the which is used for the power converter analysis, power semiconductors, or the analysis of electromagnetic components. The electromagnetic component like your electric motor, your batteries are there, your then your electrothermal reliability. So it can sustain both the electrical load as well as the thermal capability. Then the system integration. System integration means you have to build your system like the whole system is there. It is not like the only one part. Like in electromagnetics, we did the simulations of each and every part. So now we have to procure that those components inside the one module for the system integration and validate for the system simulation. Then the digital engineering is there. So in the digital engineering for the functional safety analysis, the FUSA tools is there. For the model-based system engineering, the MBSC tool is there. And for the concept EV is there also for the concept design of the powertrain. So if you have your conditions like, so you can use the concept EV tool is also there for the powertrain condition. Means the, if you have to develop your own concept powertrain, so you can design your inside the concept EV. So these are the main four models of power electronic solutions. It includes the electromagnetics, thermal reliability, system integration, and digital engineering. So we will see one by one. First, we will see the electromagnetics, then we see the electrothermal reliability, then we will see the system integration, and then the digital engineering concepts. So the power converter analysis is there. So first, we see the power converter analysis. In power converter analysis, the various power strategies are there. Here you can see the two level three phase inverter is there. This is your DC to DC converter is there. And this is your bidirectional OBC or onboard charger is there. So this is the converter example. So this type of controller design that you can develop inside the simpler window. It has the multiple access component libraries that there. So you can use the and it includes also the libraries like the VHDL components also the complex algorithms also there if you want to run your code or if you want to automate your process. So you can paste your code like your Python code or your C++ code is also supported there. So you can run through your code there. And first you have to design your power converter, like your circuit components that you have to design, and then you can do the analysis. And for the circuit simulation, platforms for the power electronics. So this is the basically we use the tools for the power electronics simulation is the circuit, the simpler one, and the twin welder. So the simpler is called whenever we are using for the like the circuit simulation, and twin welder is basically when use for the like the digital twin purpose. So that time the co-simulation purpose. Now if you want to like the model libraries also there. Here you can see it has already designed components like your IGBTs, your MOSFETs, your models are there, your motor models, your battery model, your three-phase rectifier model is already designed there. You just need to search those models, whatever the models you need, and you just extract and design the circuit on that basis. And here the languages are there, the VHDL AMS, your SPICE, and more the Python is there also there, the C language is also there. If you want a power device modeling, that components is also there. You just have the already designed components are there, and you just need to open those components and give the values that you need to give to those components so it can run by your own strategy. Then the reduce order model is there. So the reduce order model is basically the ROM models are there. So ROM model is what it basically reduce your simulation time. Simulation times means so it is like whatever their main purpose is there. So it is the zero D simulation models are there that you can see. This is the zero D simulation models used in the ROM model. So it basically reduce your simulation time. So suppose if any of your model takes the 24 hours of simulation time. So by using the ROM models, you can reduce your time by up to 12 hours or up to 6 hours. So that's the capability of that ROM models to reduce the simulation time. Then the 3D coupling part is there. So 3D coupling is basically the simulation part, the co-simulation that you can see. Co-simulations means you can simulate the behavior on the basis of the different physics. It does not include the one physics. It includes the different physics. Like yeah, if we have the electronics physics, the mechanical or thermal physics, so you can incorporate those physics inside the one window, which is the pinwheeler in terms of circuit value, and then you can see the simulation results of your co-simulation. Then the robust solver is also there. The time domain, frequency domain solver is there. The static solvers also there. You can see the waveform analysis. There are the waveform that you can develop. If you can change the values and see how the waveform is going on. Like then the application examples are there. Suppose your PMSM motor is there, where you can see the PMSM motor is there. This is the one rectifier circuit is also there that you can see the three-phase rectifier circuit and the other battery signals also there. So you can connect each and every component and see how the output is there. That you can see this is the output used by the motor model. You can see those outputs also, and you can change the input parameters and see how the output is getting changed. Next, the power semiconductor also there, and in power semiconductors, your simulation speed is right. Your you have to need the higher simulation speed so you can perform the rapid analysis and so you can change the parameters also. Like here we can see the double pulse testing. So this is basically the switching testing is there. So like if you have one switching circuit is there. So like that the switching pulse is there. So it is just like the techniques like suppose you are defining any of the current value to the inductor. Suppose you are defining the inductor current value as suppose 5 ampere. So it can the inductor will charge up to the 5, then it can pulse like how the switching behavior is there on the basis of your amplitude and frequency. So it is the measurement technique. DPT is basically the double pulse thing is the measurement, your switching measurement techniques is there. The electrical parasites are there. Parasitics mean so whenever frequency goes up to the higher level, so that times you need to calculate the parasitic parameter. So that helps also the voltage stress analysis, the breakdown voltage, and the RC is there, and the AMI/MC analysis for the conducted and radiated emission purposes. So whenever you are using the power electronics components, you need to check for the EMIMC analysis. So if there is any EMIMC is there any compatibility testings that you need to do during the simulation? So that you need to keep perform. And the multi-level modeling for the power multi-level modeling here you can see this is your PWM circuit. Okay, so it is already designed inside the power electronics. These are the component libraries. It already designed. So you can select this directly. Here you can see the no switching effects is there inside this fast emulations or long time state. So now you want to shift your circuit with the ideal switch model. Here one the ideal switch model is there, which has the higher calculation speed. Now we want to perform the dynamic analysis, the transient analysis. So you can get your components here, like this is your components, and now you have to give the input and output to specific component, and then calculate the parameters that you want to calculate. Next, the semiconductor device characterizations is there. So it includes various IGBTs, MOSFETs, and diodes is also there. You just need to give their value. Like here you can see the conditions value. So this is the data is also there, and here you can have to give the current and voltage value, and when you have to enable your component and when you have to disable your component. Like the you can see in switching the on-off circuit is there. So at this particular current value, you have to switch off your circuit. At this particular value, you have to switch on your circuit. So that you have to give there. Next, the electromagnetics component design is there. So for the electromagnetic components design, you have the components like power magnetics, DC links, bus bars, high voltage, low voltage cables that you can design inside the Maxwell. Then the electrical parasites. Here the magnetic saturation is basically the point at which your magnetic field is getting saturated. So that points also you can calculate at which point your component, your electromagnetic behavior of your component is getting saturated. You can calculate those losses also, and on the basis of those losses, you can design your strategy, your cooling strategy. The EMIMC, these parameters. So then now the multi-level modeling is there. For the multi-level modeling means you have to keep perform, and if you are designing your parameters, like if you are designing any component inside the one model, now you have to give the like the lump parameters or sometimes equivalent circuit parameters that you need to give during the transition of power electronics. So that you have to give. Yeah, the PE expert tool is also there during the power magnetics, and here the ROM model is also there. So you can create your ROM model inside the Maxwell and put this ROM model in the simpler so and in the simpler you can perform the analysis based on your circuit. You can fit the instruction by our circuit to the specific model and see the how the parameters is getting changed there, how the losses are there, what is the efficiency is there, the inductance, capacitance values are there. So that values that we have to change, like in your electric vehicles that you can see. Suppose whenever you change the conditions, like whenever you press the brake or shift the some of the parameter. So that times at in real time the controller gives the signal and in then how your efficiency is getting changed that you can see here in the post simulation part. Here the ROM model is also there. So ROM model is basically your reduce order model. It basically used to reduce your simulation time. By using those you can reduce the simulation time. So like if you are using the Maxwell tool, right? You are designing any of the component inside the Maxwell. Suppose take your traction motor. You are designing your traction motor inside the Maxwell. And in traction motor, you need to do the electromagnetic analysis. Now you can control your or give the excitation parameters. What are the excitation parameters are there? Now you want to give the excitation parameter. So you can give your excitation parameters on the basis of like your circuit. You are designing any of the circuits like in that way at this particular value, at this particular inductance value. You need to give this one the resistance value, the current value, the voltage value. And at this particular way, we have to give the excitation. So in that you can give the excitation parameters inside this implorer as to create the circuit first, and then this circuit feeds the instruction to your motor and see how your actual control of your actual running condition of your motor at the means if you are running for the transient simulation for around 1000 seconds, so you can see in first 100 seconds how the rotor perform, in next 200 seconds how it is performed. So you can see those parameters like particular way how your parameters is getting changed, and in that way how the parameters are getting performed. Next is the PCB analysis, PCB for power electronics. So like you have one of the PCB components like, and inside the PCB components if you want to do any thermal analysis or any EMI/MC analysis, so what you need to do, you just need to first design your PCB. So for the PCB and signal and power integrity calculations, the one SI wave tool is there. So in SI wave you can do the PCB analysis like it is for the signal and power integrity. Whatever the resonance analysis like impedance analysis, drop analysis, you can perform inside the SI wave. Then now you have to check the temperature control. So for that you need to use the ice pack to check the thermal parameters, like how your thermal parameters is getting used. Next, the converter and inverter is there that you can see. This is actually the PCB analysis. Here you can see. This one is PCB. Okay. Now you are done with your SI wave analysis, the signal integrity, power integrity analysis. Now you want to process with your E motor as well as the your ESV PWM condition. So that you want to. This is your PWM circuit. Now you want to connect your circuit with these inputs condition. You can see you have to connect these circuits with this parameter, and this is your SiC MOSFET condition. Then you can see the output condition also, and then you can see the overall current and voltages on the electric motor. You can see the transient voltage graphs also here according to the time for the different phases. So in this way, you have to do the this co-simulation part. You have to connect your power electronics components with the electromagnetic component. This is the E field that you can see. This is the E field is there. You can see for the gate driver of PCB, and you can perform the EMI/MC condition is also there inside the. Here you can see this is the circuit created inside the simpler. And this is your actual model. Okay, and here this one, this one, this one, these three also the actual models are there, and you can give your instruction to these models, and the output is connected there. The load conditions that you might get, the load condition, and then you can see the results. Like this is the results that you get. The radiated emission is also there. So this is basically terms related to the emission part. So this part that you can see, it is basically done for the PCB inside the SI. Next, this is the motor drive systems that you can see. So this is the graph for the motor drive system. Line to line voltage is there. Line to line voltage is there that you can see for the different conditions like VAB, VBC, VCA. This is your phases. So for each phase, what is the voltage value is there. and it is in the sinusoidal form or it is in the other forms that you can see. Just like sometimes it is in the trapezoidal form also. If you want, you can check whatever the conditions that you want. You need your voltage in the trapezoidal or in the sinusoidal, then you can see those graphs and see those graphs and take the initial conditions, like which circuits that you are connected with, which circuits that you want to connect. Like if you want the sinusoidal waveform, then you need to give the input conditions, like your lookup table values in the form of these sinusoidal waveforms. Then addressing the PWM converter and induced losses also there. So this is basically the here you can see it is the coupled phase circuit analysis. Means it includes the Maxwell HFSS as well as the simpler tool. So these three tools is getting used for the analysis of your motor drive, the PWM converter, motor drive. These three tools is used there. Maxwell is there for the electromagnetic simulation. The HFS is used tool for the various S parameters and RLCG parameters, and then this for the circuit analysis, simpler or twin bidder is getting used there. Then for the electrothermal analysis, so here you can see. So this is your EM losses. What are the EM losses that you have inside the Maxwell? You can export those losses in the iSpec, and in the iSpec you can see like what are the temperature behavior is there, what are the losses, and what are the temperature is getting there because of your electromagnetic losses. So you can, if you reduce your electromagnetic losses, then you can see your temperature plot is also becomes changing. So that you can see, and this is the actual framework is there, actual coupling, how you can call this is your actual component and this is your circuit component. You can compute the connect the circuit components to each of the input. Then you can see the output results, the output IGBT results. Then you can see the graphs like this. The actual next, bus bar harmonic loss calculations is also there. You can see. So for the bus bar applications or cable applications in Maxwell, the A5 solver is there. So basically, this A5 solver is getting used. And here, one thing is also that the two-way coupling is there. The iteration two. It's a two-way coupling. Two-way coupling means so first we do the calculation inside the Maxwell. Next, we are doing and performing the applications or performing in the ice like for the thermal analysis. So whatever the changes that you done in the simpler or in Maxwell, automatic these changes on the basis of the changes, you can see the output parameters inside the ADT iSpec means in the thermal parameters. If you change the electromagnetic loss parameters, if your electromagnetic loss parameters change, then it's supposed to have your change in the temperature parameters also. Like it has the two-way coupling. Whatever the changes that you done in one place can reflect this. You want to see or you get the reflected changes in the other part also. Now the power models for the harmonic loss calculations, solid DC-RL or AC plus RL of frequency. So this is Q3D is basically for the cable analysis. Cable means the power cables are there. Here the RLCG parameters is most important. So for that the harmonic analysis and you can perform the harmonic loss analysis here also. And here also you can connect this for the temperature plot. You can connect this with the iSpec tool. Next is the inverter electrothermal design. This is the thermal environment ROM is there. You can see the ambient temperature and this is the junction temperature that you can see. It goes around the 70 degree. Your NGBT's average temperature goes around the, at this particular frequency it goes around this one, and at this particular frequency it goes around this one. The package temperature is this one, and your actual temperature is goes, and you can see the switching losses as well as the conduction losses here on the basis of your line current. And by regarding this, you can see the your temperature value. Then the electronics reliability part is there. So we have to mitigate the failure of the electronic components. Like what are the electronic components that we have to fix. Like this is the process is the first design, build, test your on the software. If anything fault is detected, then fix the whatever the breaks or whatever the issue that comes, again tested. And if the test is successful, the fault is not detected, then we can proceed for the prototype. And here you can see 73% of product development cost are spent on this test. So this 73% cost we reduce by using the simulation software. Next, electronics reliability part is there. Here in the power electronics, you can see the how the multi-physics components are used and which of the components are used. For the electrical simulation part, power integrity, signal integrity, joule heating losses, for the temperature loss, the thermal simulation is there, and the shear law is the commandable tool for the reliability, the electronics reliability. If you want to check or perform for the electronics reliability, the shear law is the best tool for that reliability purposes in terms of the electronics reliability. Then what are the this is the summary of our session. Like we are compared the solution for the power electronic simulation, integrates the electromagnetic, electrothermal reliability, system integration, and the digital engineering. We are gain about knowledge about the ROM, what is the ROM, and why we use the ROM models for the electromagnetic components inside the core simulation or in the system simulation. So now, if you have any doubt, so you can ask. If you have any of the doubts, you can ask.
Anybody wants to ask any question, you can ask, please.
In the next part, we will see one of the software demo on the Twin Builder. So I hope it's visible for everyone. Okay. Now you can see that I created some of the basic projects are there for the simpler projects. Basically, these are the power electronics projects. First, we see one of the three-phase rectifier circuit model is there. Here you can see. So we are connecting this. This is the library that you can see. This is the component library, and here are the basic elements like our circuit, passive elements, sources, your voltage sources. This is your voltage sources. We will give like here the sinusoidal waveform is there that you can see time control sinusoidal. If you have pulse triangular, then you can pick on the basis of that. I'm selecting the sine wave, gives the amplitude and frequency, phase and offset, take it as 0. Okay, so register like 10 milliohm. The 3 is also same, the inductor is also there. This is the diode to control the flow of current. Then we use one of the inductor is there. Sorry, the capacitor is there. These are the three inductor. This is the capacitor, and this is your actual load, like your inductive, your resistive load, and the actual inductive load. And on the basis of that, you can see how the Then we can perform this analysis for the 0.1 second. Now we will see the result. Like your resistor voltage, this is your voltage sources, and this is the maximum voltage, which is around 326. Smoothing capacitor. Like you can see here, the capacitor voltage is not smoothing it. Okay, here the load resistor current. You can see the filter. The filter means here you can see this voltage is not smoothing. Okay, so that's why what we are going to use. We are using the parametric setup and set up one of the value for the your capacitor, like for the 1 microfarad, 2 microfarad, 3 microfarad up to 10. You can switch, and now you can see your actual voltage is getting smooth. Your first conditions voltage is this one. So now you can see by changing the or parameterize the capacitor value, the your voltage is getting smooth. So in that way, you can change the values to get the smoother current plots. So whatever the current plots you need or the voltage plots you need, you can smooth your voltage plot. Then the load register value that you can see if you are changing the load, what is the value of that load resistance, how it is going to be changed by using the different capacitor values. So you can say that also. So here basically what we did is this is your C filter, okay, capacitor, and here in terms of capacitor value, we give the value like C filter, and here these are the values we assign like 1 microfarad, 2, 3, 4, 5 up to, then we assign there, and then we can see the result. So this is one of the basic rectifier circuit. Now we see one of the DC circuit is there. This is the actual motor control circuit. So this is your actual motor. Okay. So for this actual motor, here this model is available in this, like here basic elements. You can see the physical domains, magnetic. You can see the components also there, like the tools, measurements, circuits also there. In the circuit, you can see the electrical machines, alternator, DC machines that you have here, DC machine. You can, I just pick up this one. This DC motor I can pick up and connect my rectifier circuit with this motor. Rotor speed that you can see. What is the change in your rotor speed? This is your actual rotor speed is at 2866. Armature current, capacitor voltage. You can see the capacitor voltage, and this is on the basis of the, if we change the capacitor values, then how it is going to be changed there. So these types of analysis that you can see, and it includes the transient condition as well as the, here it run for the transient condition. So if I'm running for the no load condition, for the no load conditions, what I am getting, I'm just using the time step as your time step as 0.1, and the end time is the 1 second. So we can get the results like rotor speed or your armature current that you can see. Suppose this is your rotor speed, okay. So here I am changing the no load condition. In the no load condition, what is the actual? In the TR no load, you can see how your actual RPM is there. The maximum RPM is around 9,852 RPM is there. So in this way, you can perform the load as well as no load condition or no load analysis. The same motor is there now. You can see this one, but this is now controlled by the, here. The third one is there. It uses the, yeah, this is the hysteresis controls that will use for this one. Okay, so in the hysteresis control, what is the way that you can see the rotor speed that you can see it is changing. Right now the car is getting smoother there. Okay. Last one is there. Here we use the feedback system, the PI controller system. Basically, it is like the feedback system. You can see it has the output like the rotor speed like this. You can see. So you have to make this component, make this circuit like this. So here you can see I am giving the output like the whatever the current is there. You can see the armature current. So armature current you can give here plus some this is your limiter values. This is your E gain as well as your I gain, and this is your motor speed as well as this is your reference speed. Can give the reference speed as well as the motor speed and see the output, how the RPM or the how the output is getting changed there. So if you have any doubt in this, suppose if you have any doubts regarding the software or any simulations, so you can directly ask. Show you one of the open examples is also there. And the power converter is there. And the rectifier circuit is also there. The control source. This is the one of the PWM circuit is there. I'm opening this one. This is the rotational electromechanical converter is there. So this component is available in the tools. Like here the multi-physics tools are there, hydraulic, mechanical system, power systems are there. You can use the components there and you just give the parameters. Like what are those parameters are there? You have to give those parameters. Okay. If you have any doubts regarding these simulations, here also I am running this one. See it looks like the electrical quantities, current ampere you can see, voltage and current on the basis of time, power comparison. So the mechanical quantity also there. So what is the mechanical power that you supply and how it's convert into the electrical power convert into the mechanical one that you can see there. What is the energy? Simply the energy that you give in terms of electrical energy and what is the mechanical power that you get. You can simply simulate that one and see what is the efficiency of that one. How much the electrical power is getting converted into the mechanical power that you can see there. So now this is basically one of the demo for this webinar. So if you want to have any questions, if you need any help or if you have any of the questions or any case study, so you can ask, can discuss about this.